10.5, example 4. And this is 4a. Oh, nice big one. K equals 1 to infinity. K to the fourth minus 2k squared plus 3 over 2k to the sixth minus k plus 5. Okay, it says using the limit comparison test. So I need to compare this to something. So I'm going to say, who's going to win on top? K to the fourth would win on top. So this series, k to the fourth minus 2k squared plus 3 over 2k to the sixth minus k plus 5 is going to be similar in shape to k to the fourth over 2k to the sixth, which would then reduce to 1 over 2k squared. So I'm looking to compare it to a 1 over 2k squared. Well, the series 1 over 2k squared is a p series. The 2 is not going to affect it. And it's going to converge because p is greater than 1. So p series converges. Okay, so now I need to look at the comparison test or the limit comparison test. And actually for this one, it's going to be hard to decide which one is bigger when you start subtracting, because normally I would now say, oh, it converges, so the other guy has to be smaller, but I can't guarantee when I put the negative 2k squared and the 3 and the negative k plus 5 in there that it's going to be smaller. So I'm going to use the limit comparison test. So I'm going to write it as the limit as k goes to infinity, and it's going to be k to the fourth minus 2k squared plus 3 over 2k to the sixth minus k plus 5 over what I'm going to compare it to. And I'm actually going to compare it, I'll get rid of the 2, make it a little easier in my brain. Just compare it to 1 over k squared, because it's already converging, so dividing by 2 is not going to affect it. And so now let's look at this. We'll turn this into the limit as k goes to infinity. We'll rewrite this as k to the fourth minus 2k squared plus 3 over 2k to the sixth minus k plus 5 times a k squared. Okay, if I do that, I'm going to go ahead and distribute it, even though you should be able to see this. K to the sixth minus 2k to the fourth plus 3k squared over 2k to the sixth minus k plus 5. The exponents are now the same on the highest degree, so the coefficients are 1/2. 1/2 is between 0 and infinity, so this has to do the same thing as the p series and therefore converges. And this is the limit comparison test. I'm going to abbreviate limit comparison test. Part B, this one's interesting. Summation k equals 1 to infinity natural log of k over k squared. And they want us to use limit comparison test. Well, we know 1 over k squared converges. But we also know that 1 over k diverges. And this one is in between those two. So we've got to figure out which way we're going to work it. So we're going to look at each of them because bad things are going to happen here. If we look at the 1 over k squared, then we would have to say the limit as k goes to infinity of a to the k over b to the k would be the limit as k goes to infinity of ln of k over k squared over, we'll use the 1 over k squared first, which then turns into the limit as k goes to infinity of the natural log of k, which, even though it's slow, it approaches infinity. All right, so the rule said if you get infinity, and the one you're comparing it to diverges, but the one we're comparing it to converges. So rule number 3 does not work. So this is inconclusive. So this is a bad, no good. Okay, so let's try the other guy. Let's do the limit as k goes to infinity, and let's compare ln of k over k squared with 1 over k, which ends up leaving me with the limit as k goes to infinity of the natural log of k over k. And as k goes to infinity, the bottom is growing faster than the top, so we're going to go to 0. All right, well, that's part 2 of the limit comparison test. And it says if the limit is 0 and the one you're comparing it to converges, but the one we compared it to diverges, so it doesn't work again. So neither one of those options are good. So we need something between 1 over k squared and 1 over k. And a logical choice would be to pick 1 over k to the 3 halves. Summation of 1 over k to the 3 halves. Still a p-series. It is convergent because p is greater than 1. And so let's work with that. So now it's the limit as k goes to infinity, natural log of k over k squared over 1 over k to the 3 halves. And let's see, that reduces to the limit at k goes to infinity, natural log of k over k to the 1/2. Okay. I could do this by inspecting it and saying it goes to 0, or remembering that natural log of k grows slower than any power of k from the growing slower section. And so now I could say it goes to 0, but you could use L'Hopital on it, and you'd get 1 over x and 1/2, or 1 over k and 1/2 k to the negative 1/2, and simplify it, and you'd still get 0. So if that's the case, now I look at the 0 rule, and it says if you get 0 and the one you compared it to converges, and it does, then this guy has to converge as well. So I can say, therefore, the summation k equals 1 to infinity natural log of k over k squared converges by the limit comparison test. That was a pretty ugly one. That concludes section 10.5.